When that turned on in 2010, we really didn't know what we were going to find. It might have taken many years to figure it out. But what do you know? The simple standard model with just one Higgs field is close enough to right. Not necessarily complete, but it's close enough that all the data we have so far, from the discovery in 2012 of the Higgs boson, the particle of the Higgs field, to all of the detailed studies that we've been making as we've been producing hundreds of thousands of these Higgs bosons and studying their various properties and so on. So far, this simple standard model with just one Higgs field that does the whole job is consistent with data.
Professor Matt Strassler, thank you for joining me today.
Thank you for having me.
So you've written a book called Waves in an Impossible Sea, and you go through what seems to be building up the idea of how the world is made up of fields or waves and fields, but you do so in a way that does not sacrifice accuracy, which is unusual for science communication. And I thought that was a tremendous effort into writing this book. But before that, and diving into the concepts and the topics of the book, I wanted to ask you first, what was the motivation for writing this book?
Well, in a sense, the original motivation was that the Higgs boson was discovered in 2012. It was one of the great discoveries in particle physics. It had been long anticipated, showed up on the front page of the New York Times. And then there were the explanations for the public about what it was about and what it meant. And they were all wrong uniformly. Some were really wrong. Some were just, mostly wrong. And it seemed to me that, that's really a failure of the physics community. We can make discoveries of such great importance to human knowledge, and we cannot find a way to convey them accurately. That's really something we need to deal with. And okay, I understand, sure, you're talking to a reporter, you've got 30 seconds. It's pretty hard to give the right answer. But then when you actually look at the books which were written about this important discovery, they too finesse the question. And there really was no correct explanation. And so I felt I knew how to give a correct explanation. I didn't know how to give it in 30 seconds in a way that would really convey much. And I also didn't find that I could quite convey it in a 1-hour talk. That was just a little too short. But I knew I could do it in a book, and I knew I could do it without math. And so it seemed to me I should try. The interesting thing is that although that was the central focus of the book initially, and for many people who already know a lot about physics, and including much of your audience, it'll be that second half of the book that gets into the details of the Higgs field and how it works and what mass is and all of that. That'll be of the most interest. But what I found was that in order to tell the story correctly, I needed to explain all of the really foundational ideas of what today we call high energy physics. I needed to explain relativity, not in detail, but as Galileo understood it and as Einstein revised it. And I needed to explain a couple of very basic things about quantum physics. Not all the complications with, interference and measurement and so on. But just enough to get us to an understanding of what the things we call particles really are. And so the book in the end became the story of modern physics, with the Higgs field as not really an afterthought, but as a subplot. And so it's a tour of modern physics from a certain perspective where I'm not covering all of it, but I'm covering all the parts you need to know in order to be able to understand what mass is and why the Higgs field can affect it.
Great. So like you said, in order to understand the Higgs, you have to go through this journey of understanding more basic concepts and sort of building up your way, because most people might be familiar with the idea that, the Higgs gives things mass. But what is mass in the first place? I mean, you have to understand what that is before you understand what is the Higgs doing and why people had to theorize its existence and so on and so forth. So maybe we can start there to set the stage. The concept of mass is maybe first encountered in Newtonian physics, where people are learning about motion and the dynamics of moving objects. Perhaps, the two giants of physics are Einstein and Newton, and their two most famous equations are F is equal to ma and E is equal to mc squared, and both of those equations have that mass term in there. So maybe we can start there. What is the concept of mass, or how did classically people view this concept of mass, and how did it evolve later on into the relativistic concept?
Well, the real starting point for this whole story I mean, in some sense, it historically goes back into to 1,000 years ago when people were first trying to make sense of motion, and most of them getting it wrong, but some of them getting it kind of right. And but the person who put it on the footing that it needs to be on is Galileo, another one of the giants, because Galileo understood the principle of relativity first, and Einstein modified it but kept it in its original Galilean form. And in a way, the principle of relativity a la Galileo, which is the statement that if you're in a closed room and you don't have any access to the outside world and you're in steady motion, there's no way, no experiment you can do which can help you determine whether you're in motion or you're stationary, or which direction you're going in or how fast you're going. And in fact, the whole concept inside that bubble of what your speed and motion is, it's actually meaningless because there's no way to even define it. And that idea has survived through special relativity and through general relativity in a modified form, but in a way it's the oldest law of physics that hasn't been modified. And it's also one of the most mysterious laws of physics because it's a very curious thing that we now live in. We now think of ourselves as living in a cosmic world where the space we live in seems to do interesting things like expand and ripple and bend. And yet, if Galileo's principle is true, you can't tell if you're moving with respect to this seeming thing. And so making sense of a universe in which Galileo's principle of relativity is true, and yet space seems to have these dynamical properties, is not trivial. And nobody knows in some deep sense why Galileo's principle is true. It just seems to be. So that is the first and the starting point. And a sort of consequence of that, or a corollary of it, is Newton's first law, which again, Newton didn't invent. It was in the air and the various people thought about it, but he put it as a principle in his set of laws. And that is the principle that if you set something off in steady motion, it will continue in steady motion unless something happens to it, right? Instead of Aristotle's notion that the natural state of objects is to be at rest, Newton says to be, and that's necessary in order to be consistent with Galileo's relativity, that the natural state of objects is to continue in straight lines at constant speed. And then Einstein comes along and says, well, yeah, but if they're subject to gravity, it's still a straight line, but with respect to some curved spacetime. But it's still kind of the same idea. There's some sort of natural state of things, which is about which is a consequence of how relativity works. And so the notion of mass is tied up with the question, what does it take to make something not move according to its natural state? What do you need to do to cause something to not move in steady motion? And so Newton's concept is a concept of force. That notion gets changed over the years. But anyway, the basic idea is you do something to an object that's in steady motion, and that motion changes. How much does it change? That's the acceleration in F equals ma. And the relationship between how much effort you made to change the object's motion and how much that motion actually changed, that's the mass. The more mass, the less effective your attempt to change the motion will be. Now, in Newton's time, you didn't have to put all sorts of footnotes and addenda on that. You didn't have to say, well, wait a second. How fast is the object going? How fast am I going relative to the object? Am I pushing it along its direction of motion, or am I pushing it sideways? I don't have to ask all those questions because F equals ma just always holds, no matter what F is and no matter what A is. But then Einstein comes along, and he and others soon realize that in the context of special relativity, this is no longer true. This definition is ambiguous. And so when we enter Einstein territory, we have to decide, okay, are there different types of mass? Certainly, there are different operational definitions of mass. Which ones should we focus on? Which ones should we use? And that becomes a long story. But the basic idea that you're taking something, you're trying to change its motion, you're looking at how effective you are, and the mass, if mass being big means you'll be ineffective and vice versa.
So in relativity, there's a common idea that as the object moves faster and faster, it becomes harder and harder to change its motion. So people usually refer to this as the idea of a relativistic mass, in the sense that the mass is increasing as an object moves faster and faster. But if you ask a physicist, they would shy away from using such a concept. Why do physicists not use this idea of relativistic mass these days, and what is it replaced with?
Well, I think one should say more precisely that some physicists would still subscribe to it and others would not. It is still debated in the community. But for a particle physicist, there's a very clear reason why we do not use the concept of relativistic mass. And that has to do with the basic structure of Einstein's special relativity. And To understand this, it's important to think about energy, momentum, and mass and how they are related. And so, in particular, there's already a difference before we get to Einstein, just in Newton's laws. There's a difference between momentum as a vector and momentum as a scalar, that is a number. What's the difference? Well, momentum is a certain amount of motion in a certain direction. That's a vector. It has components. If I change my axes, the components change. But there is a quantity which doesn't change, which is the momentum vector dotted into itself, the square of a momentum vector, or the square root of that being the absolute value of the momentum vector. And that quantity doesn't change if I change coordinates or I rotate the momentum. The length of that vector, the total momentum as a scalar, remains a constant. And so there's this difference between a vector whose components change depending on your coordinate system and a scalar quantity that you build by taking the length of that vector, which doesn't depend on your coordinate system. In relativity, the whole structure of the theory is based around the idea that there are vectors with 4 components rather than 3. That's our 4-dimensional space-time showing up. And those vectors have lengths also, although the length is a little weird because it's got a minus sign in the definition. It's not your standard length in Cartesian coordinates. You've got to deal with this Minkowski coordinates, which have funny minus signs, but it's really the same kind of idea that there's a vector that you build, for example, out of energy and momentum. Momentum is a 3-vector with 3 components in ordinary space. But when we go to space-time, energy and momentum together form a 4-component vector, energy and the 3 components of momentum. And the length of that vector squared is the square of the energy minus the square of the momentum times the speed of light squared. Now, what is that length? What is this e squared minus p squared c squared quantity? Well, if you take the square root, that's the length of the vector. That is equal to the mass of the object times c squared, where mass, in this case, is the quantity we call rest mass or invariant mass. Why do we call it rest mass or invariant mass? Well, we call it invariant mass because, like the length of a momentum vector in ordinary situations, the mass which appears in this equation e squared minus p squared c squared equals mc squared quantity squared, that mass is independent of what coordinate system you use. So if I rotate my coordinate system, change the direction of the momentum, the mass stays the same. But in fact, even if I change the coordinates in a different way, if I consider the energy momentum from my point of view, and then I reconsider it from the point of view of somebody who's whizzing by me at half the speed of light, that other person is going to measure a different energy. They're going to measure a different momentum, but the length of that vector, the invariant mass, will be the same. So again, just as we have vectors and they have components, but the length is invariant under rotations, we have energies and momenta. They depend on a person's point of view, which depends on the coordinate system that gets used, but the length of that vector, the invariant mass, does not. And so the invariant mass is this very special quantity because it is a Lorentz invariant, and all observers agree upon it. So when we say the mass of the electron, and we don't put any qualifiers on it, and there's a number there that everybody agrees on, we're talking about the invariant mass. And we call this the rest mass because if you think about it, if an object is at rest relative to you, that means it has no momentum. And then the equation e squared minus p squared, et cetera, becomes E equals mc squared. So for a particle at rest, the energy of that particle is equal to its rest mass times c squared, hence the name rest mass. Now, that defines some quantities that are really well defined: energy, momentum, and rest mass. So where is relativistic mass? Well, relativistic mass, as it's usually defined, is E divided by c squared. It's the statement that E equals mc squared no matter how fast a particle is moving if m is relativistic mass. Now, E and P form together a 4-component vector whose length is well defined. Relativistic mass is E divided by c squared. But that means that relativistic mass is not a relativistic invariant. It's not a Lorentz invariant the way rest mass is. Depends on your perspective. And that means it should be part of a 4-vector because, otherwise, what happens to it if you change coordinates? You have no way to understand that. So it should be part of a 4-vector. And since the relativistic mass is energy divided by c squared, there must be some quantity which is momentum divided by c squared, which combines with relativistic mass to make a 4-vector. There is no natural concept that's just momentum divided by c squared. So relativistic mass is sort of an orphan concept. It doesn't appear in a 4-vector, and it's not an invariant. And when you think about it, it's just a restatement of the energy and the momentum, just divided by c squared. You're not adding anything by calling it relativistic mass. You're just adding a concept that isn't needed. You already have energy, and you already have momentum. You just divide by c squared. So from the point of view of a particle physicist, this is a redundant concept. It's not really naturally organized into some sort of relativistic four vector. And you can just avoid it and use energy instead. And everything's much clearer that way. So that's basically the fundamental reason why particle physicists avoid it. You can define it if you want, but it doesn't really buy you anything. And if you think it has something to do with gravitational mass, which is also not an invariant concept, maybe that gets you closer. Well, it doesn't really. So the fundamental issue is that this is an unnecessary concept. It doesn't add much, and it tends to confuse people. But of course, what happens is that in the media, I should say, where this comes from is that Einstein himself originally thought this was the right way to think about it. And then he kind of went back and forth. And towards the end of his life, he had come to the conclusion that is more along the lines that particle physicists today use. But many other people by that point had adopted relativistic mass as an important concept, and they still use it. So, I don't really care as long as you understand that there's two different types of mass here. And when you're explaining things to the public, you better make clear which one you're talking about. Because there's one type of mass that increases with speed, that's the relativistic mass. And there's one that does not, and that's invariant mass. And you better make sure which one you're dealing with.
I once heard a statement describing relativity that says that relativity is more about finding things that are not relative to different observers. So it's about finding those things that are invariant, like you said, under Lorentz transformations. And that, I think, was a pretty apt way of describing what the goal of ultimately relativity was. So mass, for example, was an invariant. Maybe the speed of light was another.
That's the most important, right? I
mean,
speeds are always relative, except that the speed of light relative to everybody is c. That's a very strange statement. It's true.
Yeah. So then we're going to stick to this concept of mass and relativity. It still exists, and it still, in a sense, describes the object's resistance to motion. Or, as you put it, if you apply a force on an object, you're trying to change its motion.
Yeah, I think. Sorry, let me just step in for a sec. The key point being, and because I didn't say this, I should stress it, is that again the resistance of an object to a change in its motion depends now in relativity on how fast that object is going and what direction the force is that you apply to it. Rest mass is the mass that you measure if you and the object are stationary to start with, and you give it a push from rest. So in the end, it comes back to F equals ma as long as you're stationary with respect to the object when you do the experiment. And the interesting thing is, even though I've stated that in terms of being at rest relative to an object, we all agree, no matter what our perspective, on who is at rest relative to the object. And so we all agree on the answer. What is the rest mass? That's why it's an invariant.
Great detail there that was missing in my statement. So I want to now dig deeper into this concept, and I want to try and get to the bottom of it, get to the origin of the idea of mass and where it comes from. So I want to get small now. We talk about everyday objects, they're macroscopic, but we know they're made up of smaller and smaller things. And we know that smaller objects, like you mentioned an electron, also has a mass. So these particles have this property of mass, but to understand maybe where that mass comes from, first we want to understand what are these quantum particles, what are these objects. So let's maybe zoom into quantum mechanics and try and understand the nature of quantum objects. So how can I begin to understand, maybe you can take us on a journey through the quantum revolution of beginning to understand the nature of a quantum object first?
Well, I'm going to rephrase your question slightly for the following. Quantum physics is a general framework. Like Newtonian physics is a very general framework. It's capable of describing all sorts of different things, which may or may not have anything to do with the objects in our universe, or may or may not have anything to do with objects that can move around and are particle-like. So quantum mechanics is the application of quantum methods to mechanical systems. And the language of particle physics is called quantum field theory, and that is the application of quantum methods to fields. We'll talk about what fields are in a minute, but quantum objects could be many different things if they're just called that. So what you're really asking is, what are the quantum objects that we and all the stuff around us are made out of? What is the nature of the objects in our world that are described by quantum physics? And part of the complication of answering that question is that most people who get some training in physics, but don't go on to become experts in particle physics or in solid state physics or in some areas of astrophysics, they learn quantum mechanics of third year undergraduate teaching. Right? So third year undergraduate class, you get your quantum mechanics class. Then you may learn some applications of quantum mechanics like quantum chemistry, but you're not going to go into quantum field theory. That's not necessary. And the problem is that this gives you an impression of what quantum physics of electrons and atoms is like. But it's appropriate, and even some methods for dealing with the interaction of electrons with light. Although if you notice very carefully in your quantum mechanics class, you never deal with the quantum physics of the light, really. Or if you do, you do it kind of in a cheating way. And this is for a very good reason. The quantum mechanics of the 1920s, Heisenberg and his friends, and Schrödinger, Born, and even the early stages of Dirac, where Dirac was trying to deal with the problem I'll describe in a second. These methods really work beautifully for particles that are traveling slowly with respect to the speed of light. But when you try to put special relativity in, as Dirac did, he tried to write a relativistic theory of the electron, you discover that a lot of things start to go wrong. And one of the simplest things you could say goes wrong is that in a relativistic theory of electrons, you have to have electrons that can collide with each other at very high energies, or can collide with light at very high energies, and turn from one electron into two electrons and a positron. You can create a particle-antiparticle pair, or 10 of them. So your quantum mechanics, which is good for describing a fixed number of particles, now has to cope with the fact that the number of particles isn't conserved. And so now you sort of need a fancy quantum mechanics that can handle maybe 1, maybe 3, maybe 5, maybe 7, maybe 9, maybe up to infinity number of particles all together at the same time. This proves extremely difficult until you learn how to do this with fields. Quantum fields can handle all of this. And so if you start with 1920s quantum mechanics and you try to deal with relativity, you are led inexorably, although it took people 20 years to do it because it was very confusing, you are led to quantum field theory. And in quantum field theory, electrons are very different from what they are in quantum mechanics. So you've built all this intuition from your third year undergraduate class about what electrons are and wave functions, so forth. And a lot of that intuition is often quite poor because of the approximations that are used, and you get confused about a lot of things. And now you have to move all that to quantum field theory, and the whole picture is different. And so when we ask what are quantum objects, even the ones in our world, we have to ask, wait, are we using the language of quantum mechanics, or are we using the language of quantum field theory? And in the book, I focus on the language of quantum field theory because quantum mechanics does not agree with data. It agrees fine for atomic physics, but it doesn't agree with particle physics. If you're slamming together particles at near the speed of light and you're producing new particles over the place, quantum mechanics cannot handle that. You need quantum field theory. So we know quantum mechanics is an approximation, whereas quantum field theory, there is no known experiment anywhere which is known yet to disagree with quantum field theory. It may yet happen, but certainly if we're trying to gain intuition about the world, it's crazy to try to get it from quantum mechanics when we know quantum mechanics does not agree with the world. We have to get it from quantum field theory. But almost nobody knows quantum field theory because you don't learn in undergraduate classes. Most books about it for the public, or even for let's say advanced readers of science, which many undergraduates would be who don't take a quantum field theory class, but they might read about particle physics. These don't really explain what's different about quantum mechanics and quantum field theory, and they don't really clarify how the concepts change. And so one of the reasons I wrote the book the way I did is I felt that really there is no book that sort of captures what electrons are in field theory. So maybe that's good as a sort of layout. Shall we start by talking about what electrons are in quantum mechanics? Where would you like to go with this?
I think the fact that you mentioned that if we start with 1920s quantum theory, we have to then kind of unlearn it to get to quantum field theory, because then you have to introduce the idea of fields. Maybe we shouldn't pollute the minds of the listener and go through the 1920s quantum theory. Instead, maybe we can take directly the view of quantum field theory so that we start fresh, maybe, a new intuition that people can cling on to for their thinking about quantum particles.
Sure, and at some point we'll connect back to quantum mechanics, but yeah, we can do it later. And in a way, one of the nice things about quantum field theory is there are sort of two natural routes. One is you go through quantum mechanics and then you soup it up to quantum field theory. The other is you go through classical field theory and you soup it up to get to quantum field theory. And those two routes have to somehow match, and of course they do. And if we're going to talk about classical field theory, then the natural thing to do is to go back to first year physics, where the one field we really learn about is the electromagnetic field. or this is the electric and magnetic field combined together by special relativity into a single field, the way we think about it today. And now the way we learn it, again, there's always this problem. When we ask, what is something? What is mass? What is a particle? What is a field? The word is is it a slippery word? I mean, are you asking, what does it do? How do I describe it? Or are you asking, what is it intrinsically? And as for the question, what is the electromagnetic field? I don't know what it is intrinsically. Nobody does. So we're going to set that aside. That's not the question I'm trying to answer. But the question that we can answer is, what does it do and how do we describe it in math? So in math, as we learn in first year physics, the electric field is some function of space and time. You give me a point in space, I can measure the electric field there. It's some vector. Okay, well, now what? Well, of course, what makes it interesting is, first of all, it responds to matter that has electric charge, and it has an effect on matter that has an electric charge. So what makes it the electric field is that electrically charged things create it and respond to it. And what makes it a field is partly the fact that it's defined everywhere. At every point in the whole universe, I can go and measure the electric field there. So there's a vector at each point in space, E of X, Y, and Z. And time, of course, can change with time. And how does it change with time? Well, there's an equation. Or more precisely, I take the electric field and the magnetic field together, and I write a set of equations. Those are Maxwell's equations of electromagnetism. And they tell me how the electric and magnetic field behave in the absence of matter and in the presence of matter. And then I also need equations which tell me how matter behaves in the presence of electric and magnetic fields. Once I have those set of equations, I'm good to go. I can solve all sorts of problems. Now, let's set aside the matter for a moment and just ask, okay, somehow I generate some behavior in the electromagnetic field. One of the things I can generate is an electromagnetic wave. And of course, electromagnetic waves constitute visible light and radio waves and X-rays and the whole electromagnetic spectrum. And I can have any combination of those waves. And so basically, the electromagnetic field can take on any shape. And I plug that into the Maxwell's equations, and I can calculate how that shape evolves over time. And if that shape is very simple, it's just a simple wave, well, that wave will continue as a wave-like structure, spreading out across space. Details depending on exactly what kind of wave it is, but there's some equation for it. It's not that hard to figure out. And from any particular observer's point of view, if I have a simple wave, that wave has a frequency and a wavelength, right? Just the standard simple sine wave. It just propagates along if it's a simple enough wave, or maybe it spreads out. If it's a wave from a central source, it'll spread out, or if it's from a distant source, it'll just progress as a so-called plane wave. The waves just all move in one direction. So okay, good. So I have a simple wave with a frequency and a wavelength and a direction of motion. Now, quantum mechanics comes along, or more precisely, the photoelectric effect comes along, and Einstein has to explain this somehow, which no one else has been able to do. And he says that, yeah, I know light's a wave. We've known this for 100 years. And people were debating it for 300 years. Is it light made of particles? Is it made of waves? And then Thomas Young discovers interference fringes. Okay, done deal. It's a wave. But then there's this photoelectric effect, which seems to say that even though the light's a wave, it isn't sort of gradually kicking electrons out of atoms. It either kicks one out, kicks another out, or it doesn't. How can these things be consistent? Einstein does not say, it's amazing how often this guy was right about things. He's such a careful thinker. He does not say light is made from particles. He says light is made from quanta, that somehow a chunk of the light doesn't tell you what shape it is. He tells you how much energy it has. It has energy equal to Planck's constant, which Planck has introduced into physics 5 years earlier. It's equal to Planck's constant times the frequency of the light. And somehow a chunk of that light goes in, finds one electron, and kicks it out.
So if I may interject real quick, Einstein never said that he imagined light to be a stream of particles. So this is sort of a misconception that people have. Instead, what you're saying is that what is discrete is the energy carried by the light, or perhaps the energy that is given off by the light.
Well, Einstein, of course, was at the time, in 1905, a little bit agnostic about this because he knew he was making a very strange statement. I mean, if light comes in packets, how can there be interference? And certainly if light were made from literal particles, little streams of little dots, that would be hard to understand. This is not what Einstein had in mind. He wasn't sure exactly what he had in mind, but he knew that didn't make sense. And indeed, nobody knew what he really meant for a while. And it took, and it wasn't really until Compton, about almost 20 years later, that people realized that photons really do have energy and momentum and mechanical notions of energy and momentum that are very similar to particles, literal dots or objects made of any sort. They have energy, they have momentum, they satisfy certain relations. The E squared minus P squared relationship holds, with m squared c squared on the right-hand side happening to be 0 for photons, but it's the same relation. So now that it was clear following Compton that these objects behave like particles, people started calling them particles, gave them a name, they called them photons. So Einstein's quanta became particles of light, photons, and I'm actually not sure exactly what Einstein's reaction to that was. I've not read anything about the way he approached this question at that time. Certainly he was about to get distracted by all the confusing things about quantum mechanics that were about to arise a couple of years later, and he had other fish to fry at the time. But the thing we always need to remember is that this debate as to whether light is made from waves or particles, that goes back hundreds of years because of geometric optics. In many ways, a flow of waves often looks the same as a flow of particles if you're just keeping track of some simple things like direction of motion and reflection and stuff like that. So the fact that the quanta satisfy an energy momentum relation that's similar to mechanical objects, that doesn't prove these things are little dots. It just proves they satisfy this relation. And if you really look at quantum field theory carefully, you never see little dots. They're not in the equations. They're just not there. So what is a photon in quantum field theory? It is really what Einstein said. It's you take your classical wave and you imagine that it's made up of chunks that have energy, but also have wavelength and frequency, just like the wave as a whole. So it's as though your big wave is made out of little waves with the same shape, but a smaller amplitude. So in that sense, you can call them particles if you like, but they don't have the shape of particles. What they really are is a sort of indivisible unit of a wave. They're indivisible tiny waves, not tiny in this direction, in physical space, but tiny in amplitude direction and tiny in energy. And that's why they can have frequency and wavelength, even though they're particles. And this is one of the reasons why I prefer the word wavicle, because the word particle, first of all, you always need to come around with your quotes or you get the wrong picture. And second of all, just even if the quotes are there, your mind is going to call to mind this image of a little dot. This is the wrong image because, again, how can a particle have frequency and wavelength? It doesn't in quantum field theory. It's a little wave, and then it's obvious it has wavelength and frequency. It's a different thing. Now, that's fine for light. What about electrons? So in quantum mechanics, we do treat electrons as particles. They have position. We don't know the position. The position is an operator or something that's uncertain. You have to, you take your wave function or some sort of description of the system, and you calculate what is the probability of finding the electron's position here or there or there. But the electron itself is not spread out according to those equations. The description of the electron is spread out, but not the electron itself. But in quantum field theory, we treat the electron the same way we treat the photon. Just as photons are these little waves, little again in amplitude, electrons are very much the same. Their difference is, of course, they're fermions, not bosons. That they've satisfied a Pauling exclusion principle. That does make them different. They're not as intuitive, but it's still true. An electron in quantum field theory has a wavelength and a frequency, which a little dot does not. And so the picture I've described using photons now gets applied to electrons and to quarks and to muons and to W bosons and Higgs bosons and all of the particles of the Standard Model. They're all described as the same type of object with just little details being different. Whereas in quantum mechanics, we treat slow objects as particles and fast objects, meaning fast close to the speed of light, we just can't deal with them. So that's a fine picture for atomic physics maybe, but if you really want to understand the world, you need to go to this field theory picture in which these things have frequency and they have wavelength. Let me give you a little example of how things are different between quantum mechanics and quantum field theory, which is particularly important. So in quantum mechanics, we use Newtonian, that means pre-Einstein, relations for energy and frequency, or for wavelength and momentum. So in particular, the relationship between energy and momentum is the same as in Newton. That is, so we say energy is equal to the momentum squared divided by 2m, which is the same as 1/2 mv squared in Newtonian language. Now that relationship is fine. So that what that means is that if you take that equation, if you say if the object has zero momentum, if it's just sitting still, then it has zero energy. So it doesn't have a frequency if it's stationary. But that's wrong. If it's stationary, E equals mc squared, right? You're forgetting relativity. Oh, right, we need relativity, right? So we replace E equals p squared over 2m with Einstein's relation that E is the square root of the momentum squared minus the mass squared. And that's fine, except we're doing relativity and quantum mechanics. You know that's not going to work. But okay, fine. So we go to quantum field theory, and now our electrons themselves have a frequency. Okay, so now I have a stationary electron. What is its frequency? What is its wavelength? Well, stationary electron has zero momentum, and it has E equals mc squared. But in quantum mechanics, the energy and the frequency are proportional, and the momentum is proportional to 1 over the wavelength. So if the object is stationary, it has zero momentum, that means it has infinite wavelength. So this is an object which is constant across all of space, at least formally. In practice, you'll never get exactly this, but it'll be close to that. So you have something that's very spread out and doesn't have any structure to it. It's just constant. But not constant in time. It has a frequency. E equals hf. So this is an object which has a frequency, and you know what its frequency is. Its frequency is related to its energy, and it's a stationary object, so E equals mc squared. So the mass of the object tells you the energy it must have, and the energy tells you the frequency. This is an object that's going up, well, not up and down in physical space, but somehow it is oscillating, and the frequency of its oscillation is proportional to its mass. That's true in quantum field theory. That's a basic concept in quantum field theory. Quantum mechanics knows nothing about this, but in quantum field theory, it's central. So just to summarize all that, again, the key point in quantum field theory for understanding mass and how it relates to particles is that a particle that is at rest, whose rest mass, therefore, is a measure of what happens to it if we kick it in some direction, see how it responds. That mass is related to how much energy it has, but because this is a quantum, this is an object which is an indivisible wave, its frequency is related to its energy, and therefore the mass is related to the energy, is related to the frequency.
So now we've made the connection between mass and the frequency of an object in this underlying field that it exists in. So I want to sort of get to the bottom of this field. So you said light exists in an electromagnetic field. And if you take the picture of quanta and now you have a quantum field, then, okay, so photons are the quanta of the electromagnetic field. How does that work for something like an electron? What kind of field does an electron exist in?
So the picture of particle physics today is that for every type of particle, there is a corresponding field. So photons are ripples in the electromagnetic field, electrons are ripples in the electron field, up quarks are ripples in the up quark field, Higgs bosons are ripples in the Higgs field, you name it. And maybe the right way to think about it is that you start with the fields. The fields are everywhere across the cosmos. And normally they're just sitting there. Well, sitting there as much as anything in quantum physics can just sit. But then there's no particles there. I can take a box and take all the particles out, and then we just have some empty space. But the empty space is full of those fields. Fields are never absent. They're just boring. But now if I take a hammer and I whack one of those fields somehow, I do something to the universe inside that box. Now the fields are going to start rippling. And those ripples, it's a quantum world, they're going to come in quanta, which we call particles. So when something happens to the universe, the way it responds is a lot of particles get made. And so that is the general picture. There are fields out in empty space. They might be doing nothing, but it's pretty easy to get them to ripple. And once you do, those ripples appear in experiments as the things we call particles, again with quotes. So this is something which particle physicists came to as an image of the world between the 1920s development of quantum physics as a framework and the 1970s, when it became clear that quantum field theory was a consistent quantum mechanical framework which could explain all of the different types of phenomena that we knew of in our particle physics experiments. And there was a considerable period of time where people weren't sure about that. But the 1970s is where it all came together and led to the development of what we now call the standard model of particle physics, which includes all the particles and forces of nature other than gravity, which is sort of added on. And that theory of nature is so amazingly good that there's not a single known experiment that disagrees with it at this point.
So if I take a look at the electron field, for example, you said that every particle in the standard model of particle physics is associated with its own field in quantum field theory. The electron has mass, the photon does not have mass. How does that manifest in terms of their frequencies inside of these fields when they are, let's say we put energy into these fields, you make a ripple. How is it different between a massive quantum field versus a massless quantum field?
Right. So, this is that's a little bit jargon. We all use it, but just to point it out, the question is, what is the difference between a field whose particles have non-zero mass, versus a field whose particles have zero mass? What is the qualitative difference? And to answer that question, it's useful to take a step back and ask, if we go back to just classical fields like the electromagnetic field, or simpler things that ripple like a string or the surface of water, or I mean, we know all sorts of examples in nature of things that like to ripple. What would it mean for something to ripple in such a way that when we go to quantum physics, its ripples would have mass? And the reason why this turns out to be both an interesting question and not a question with an immediate answer, is that it turns out that all of the fields that we encounter in physics classes and in daily life correspond to fields that, if you make them into quantum physics, their particles would have zero mass. And so there's this small amount of unfamiliarity that we have to cross. But we could have, I mean, it's not actually that complicated. It's just unfamiliar. And so in a way, we could modify our undergraduate classes to teach about this other type of field, which for whatever reason doesn't come up in nature, but we could point out that it exists. It's easy to construct one. And then it would be easier to understand what quantum mechanics fields are that give you particles with mass. So let me give you a sense for this. So the difference between a classical field whose quantum field would have massive particles versus one that doesn't is a form of what I'll call stiffness. Now, stiffness is rather an imperfect word. And the reason is they're kind of different. They're different kinds of stiffness. And usually we call stiffness as something else. And what's really missing is a word. We don't really have a word either in the English language or in the physics jargon that corresponds to what I'm about to describe. So I'm going to take my time going through this because it really is the critical issue. So we can talk about this just in terms of a string. So let's imagine, okay, my arms here are just supposed to describe a string. Okay, so there's got a string sitting here. And you know that I can get ripples to move down a string. If I wiggle one end, a wave will move down the string. And why does it move down the string? Well, there's a tension in the string, so that if I pull the string upward, it doesn't want to get pulled upward. The rest of the string wants to pull it back down. So there's a sort of stiffness of one sort which tries to keep one piece of the string from being misaligned from other parts of the string. And that's what we call stress. Okay, you're stressing the string if you pull it upwards and then let go. And that's how you pluck a guitar string, right? You pull the guitar string up, you let go, and the string responds. It responds by waving up and down. But it's critical for a guitar string that you fix the two ends. Right? So you pull on it, and now because the ends are fixed, it's going to bounce up and down on like this. There'll be some frequency, which is determined by how stiff the string is in this sense of stiffness, of the stress between one piece of string and the nearby pieces of string. But now I want you to imagine something else. Let's, first of all, remove the ends. We don't need the ends. So the string is just sitting there. It's floppy, except that I'm going to do something funny with it. I'm going to turn on some funny forces you're not used to necessarily that have the property that if I put the string here and I move the string as a whole upward, well, if it was a guitar string, and I didn't attach it to the ends, that doesn't do anything. I could just move the guitar string forward, backward, up and down. It doesn't matter. If it's not connected to the guitar, it doesn't care. But supposing there was a force that made it care and said, no, the string really wants to sit right here. And if I move it down, it wants to come back. And I move it up as a whole, it wants to come back. This is a sort of restoring force. This is something which means that the whole string doesn't want to move from its point of equilibrium, which normally a guitar string without ends is not going to have. But if we add something to the world that fixes the string's preferred position, now if I move it away from its position of equilibrium, it's going to start as a whole vibrating in a new way, not like the way it vibrates in a guitar string, because there the ends are fixed. But here, even without fixed ends, it's going to start vibrating due to this restoring force. It's not so different from having a pendulum, and you move the pendulum bob to one side, and the whole thing just goes back and forth. Now we've got this whole string going back and forth due to a restoring force. The stronger the restoring force, the faster the oscillations are going to be. So the question is, if I look at a field, again, even just a classical field, not before quantum mechanics, if there's no restoring force and there's nothing fixing the ends, I can just give it a push and it'll just gradually increase. But if there's a restoring force and I give it a push, well, it's going to come back. And so there's a frequency, sort of natural frequency for this field, which depends on the restoring force. Just as there's a natural frequency for a pendulum. The stronger the restoring force in a pendulum, which depends on gravity and how strong the string is, the faster the oscillations are going to be. Stronger gravity, the thing's going to oscillate faster. Well, okay, so if I have some sort of stronger restoring force, my field is going to oscillate faster. Now, what does this oscillation have to do with particle physics? This has all just been classical. Now we go to quantum physics. We say, okay, this is a sort of wave. Einstein's going to tell us it's made of quanta. What is one quantum of this wave? Very small amplitude, but same frequency. Well, that quantum is what we call a particle of some type. It has a frequency, therefore it has an energy, therefore it has a mass. So the stronger the restoring force that the field experiences, the faster is its resonant frequency, the larger is the energy of one of its quanta, and therefore the larger is the mass of one of its quanta. So the mass of the particle depends on the strength of the restoring force to which the field is subjected. And that restoring force is something we can talk about in classical physics. That's not a quantum phenomenon. The quantum part is turning that into a statement about the particles, the quanta. So if you go back to your second year physics class and you study a string or you study a trampoline, or you study some physical object that's not got any quantum physics, but it can ripple. And you take away the ends, you just let this thing spread out across all space. But you add this type of restoring force, you will see there's a type of standing wave, a wave that's not going anywhere. It doesn't even have any structure. It's just constant across space, but it changes with time. And that wave is a solution to the equations. It was there the whole time. Just nobody taught you that because nobody bothers because, again, we don't see these examples in nature very much. But it is this simple example of a classical field, which is the one we need for particle physics because all of the fields other than the electromagnetic field and one or two others, all of them have this restoring force. And that restoring force is the reason why the corresponding particle has a mass. And so the top quark has a much larger mass than the electron, or I should say the type of particle called the top quark has a mass much larger than the type of particle called an electron, because the top quark field is a much stronger restoring force than the electron field does. That's how it works. It's not really that complicated, but somebody's got to sit you down and show you how it works. So that, again, was part of the point of the book. I don't do it with math, but I do it with concepts. On my blog, I do have it with math for those interested in following along. It's not that hard, and that's again one of the points. It's sort of a gap in our educational process. It's not that this is that complicated.
I think that was extremely beautiful because you just laid it down in very simple terms, and yet really no accuracy was suffered there. You really took us step by step through understanding what is the difference between the classical picture and then this sort of, for now, mysterious restoring force that is added onto these strings. So I want to get there to this mysterious restoring force. But before that, you mentioned something like a top quark. You mentioned W bosons. Can you take us through a tour of this particle zoo, the standard model of particle physics, just so we can kind of lay the land of
groundwork.
The groundwork of what kind of particles exist according to our best understanding right now.
Sometimes people misunderstand Occam's razor. Occam's razor sometimes, it's something to do with choosing the simplest explanation for a phenomenon, but it is not the statement that the world should be simple. And the standard model of particle physics is not at all simple, elegant, pretty, unless you decide you want to see it that way. It does indeed have a zoo. There's a whole bunch of different types of particles. And when you try to make it as pretty as possible, then along comes this thing called the Higgs field, and it makes it just a total mess. But you can organize the standard model in the following way. So again, the standard model does not include gravity. Gravity is sort of an add-on, although gravity is a field theory too. It is not completely outside of the framework of quantum field theory. It's just that we don't have a complete theory of quantum physics for gravity. At least we have candidates. We don't know which one is right. So setting gravity aside, you take the other types of forces that are known. The electromagnetic force, the strong nuclear force, which is what holds quarks together in protons and neutrons, the weak nuclear force, which is responsible for various forms of radioactivity and supernovas, and there's another force, which is the Higgs force, but people often forget about that. But okay, I'll set the Higgs field aside anyway. You take the three forces I just mentioned, and for each class of each of those three classes of forces, there are some fields. For the electromagnetic force, there's an electromagnetic field. For the weak nuclear force, there are W and Z fields. For the strong nuclear force, there are gluon fields. Okay, so we got those three sets of fields that are associated with forces. And then there are some electron-like fields, electron-like in the sense that the particles that are associated with them are fermions. The particles associated with the ones I just mentioned are bosons like the photon. The fermions include the electron, and so there's an electron field. The electron has two cousins, which are particles which are heavier, and there are corresponding fields with more stiffness or more of a storing force. Those are the muon field and the tau field, cousins of the electron field. So we've got three of those. Then there are three neutrino fields, which only interact with a weak nuclear force, so they're hard to measure, but we know enough about them now to know a great deal, actually. And then there are six types of quarks that come in three. There's three pairs of there's three sets of each. Up type quarks, which include the up quark, the top quark, the charm quark. There's a field for each one. And then there's a bottom quark field, a down quark field, a strange quark field. And so those 12 fields, the electron and its two cousins, the three neutrinos, the six quarks, those 12 fields are the fermionic fields of the Standard Model, and they all interact via one or more of the electromagnetic weak nuclear or strong nuclear force. And the pattern of who interacts with who is fundamental to the structure of the Standard Model. We don't need to go into those details right now, but it's fairly simple. To this, we add the Higgs field. And the Higgs field interacts with most of the other fields. And the thing that makes it special is that whereas, for example, the gluon fields interact with all six of the different types of quark fields in exactly the same way, the Higgs field interacts with all of the different types of fields, each in its own way. So there's this huge number of quantities which describe how strongly does the Higgs field interact with this neutrino field? How strongly does it act with that quark field? How strongly does that interact with the W boson field? Each one of these is different. So the simple structure of the Standard Model with three different forces and four classes of fermionic fields becomes a total mess when you put the Higgs field in. And that's the Standard Model. And it's nobody knows where it comes from. It's a mess. We don't know why it has three different types of forces of the sort I mentioned. There's also the Higgs force, and the Higgs force is this mess because of all these different interactions. We don't know why there's four types of, why there are neutrinos and electron and its cousins in the two different types of quark fields. And we don't know why there aren't other fields and why there aren't multiple copies beyond three of the ones we know. It's just experimentally true. This is what we find in nature. And these are the equations that successfully predict all the things we find in nature. And that's the Standard Model, and we're sticking to it for now. But if somebody came along and told me there's much more to it, there's all sorts of particles and fields that we're missing, there's maybe some overarching structure we know nothing about, I wouldn't be the slightest bit surprised, because this is a structure which works, but has almost no explanatory power in terms of what we have no idea what the different masses of the part. We don't know why the particles have different masses, or why they have the specific masses they do. We don't know why the forces have the strengths they do. These are just facts we know from experiment.
If I take a look at the history of putting together this particle zoo, at some points in time, there was motivation and reason to expect that there is some particle out there that we have to go look for. Maybe in the case of the neutrino with Wolfgang Pauli, but then there's some other examples of the Standard Model where a particle just appeared. I don't know. No one was expecting that. Famously, I think it was the muon that was it Isaac Rabi who ordered that. People were not expecting that. But this final particle that you talked about, the Higgs, or we should say the Higgs field, that was something that was actually predicted. There was a lot of work that went into it in the 20th century, and then until 2012, which is very recently in physics times, it was discovered. So the Higgs was kind of special in the fact that it was predicted. People thought that this thing should exist. Why did they think that?
Well, before I answer that, let's step back a little bit on the history, because I think your perspective is not unreasonable, but there's, I think, some nuance which is interesting. So, in a way, the Higgs field was maybe not the most clearly predicted of the various types of fields, even in my lifetime. So, for example, we were much more confident that there was a top quark field before we discovered the top quark than we were that there is a Higgs field, at least a single Higgs field. And the reason is that once we discovered the bottom quark and understanding the structure of the Standard Model, you really can't have the bottom quark without a top quark unless the Standard Model structure is wrong. And if that were true, the bottom quark would have properties that we don't observe. So once the bottom quark had been found and studied to some degree, we kind of knew that the whole thing doesn't make sense unless there's a top quark. And you could stand on your head and kind of get around that, but you had to work pretty hard. So there have been times where the structure of the Standard Model is so tight that you kind of knew there had to be another particle. And there have been other times where it hasn't been tight at all. So for example, once we'd found one heavy cousin of the electron, and we'd found three quarks, the up, down, and strange quark, it wasn't obvious there was going to be a charm quark yet. And it also wasn't obvious at all there would be a a second cousin to the electron, the tau. And so both of those were to some degree surprises, although there was some prediction about the charm quark in advance, which is a subtle issue which I won't get into, but it was a very clever one. And so in each stage, sometimes there's been total surprise. Other times there have been suggestions that something might be there, but not everybody was convinced. And so it required experiment to settle it. Now, what was the situation with the Higgs field? So the fundamental problem in the Standard Model as of the 1960s, when Steven Weinberg and then Abdus Salam first tried to grapple with what we were learning about the weak nuclear force and its structure, and what we knew about quantum field theory and its structure, was sort of the following. First of all, because of the structure of the Standard Model, it turns out to be very hard to both give the electron and other similar particles like the quarks, although in the 60s they didn't know about the quarks yet, but it turns out to be true. Or they weren't sure about the quarks, I should say. But for the electron, we know it has weak nuclear interactions. We know those violate a symmetry which is called parity, where you flip the universe in a mirror. We know that the way an electron which sort of spins this way is different from an electron that spins this way. That's a little complicated, but basically, you see these measurements. You see in experiments that it matters which way the electron is spinning. You don't get the same interactions. The violation of parity was discovered by C.S. Wu at Columbia University, and shockingly, she did not win the Nobel Prize for this. But this is an experimental fact from the 1950s. And once this was known, it's not that long before you realize there's a problem, which is that you cannot write down a mass for the electron, or even more precisely, a restoring force for the electron field that is compatible with the weak nuclear force. They don't go together. You can't have the parity violation on the one hand and the mass term on the other. Furthermore, people were beginning to have some guesses about how the strong nuclear and weak nuclear force might arise in the early 1960s. And Glashow had developing on ideas from Schwinger, his PhD advisor, and from Yang and Mills a little before them, had the idea that maybe the weak nuclear, just like the strong nuclear force, the electromagnetic force has to do with an electromagnetic field whose particles are photons. And it's long range because the electromagnetic field does not have a restoring force, and the photons therefore are massless. Maybe the weak nuclear force is weak because it's a short range force, and the short range comes from the fact that there are W fields and maybe a Z field too, and they do have a restoring force, and that makes their particles, gives their particles a mass. And the restoring force has the effect of shortening the range of the force. But Glashow just sort of put the restoring force in by hand. And people also sort of knew that didn't quite make sense either, because you couldn't make that consistent with certain aspects of the mathematics. And meanwhile, Higgs was beginning to think, along with Broughton Engler and Guralnik, Kibble, and Hagen, about some ways of allowing photon-like particles to get a mass, or electromagnetic-like fields to get this restoring force. And Weinberg put this all together, as did Salam separately, so that you could have a theory in which W bosons might exist, and the Z boson might exist, the W and Z fields might exist, and they might get a restoring force from a field of the sort that Higgs and Broughton Engler had invented. And the same field would be able to solve the problem of the electron fields restoring force and give the electron a mass. So Weinberg sort of took all these pieces and put them all together, where you could have one theory in which you have a weak nuclear force that's short range, because the W and Z fields have a restoring force, they have stiffness, with the W and Z bosons therefore having mass, and the electron field can have a stiffness and therefore have a mass, and the muon field can have a stiffness too, and it's a different number, so it can have a different mass. And the whole thing starts to fit together, and it didn't quite work because the quarks didn't work quite right, but that's because he didn't know about the fourth quark, the charm quark. Well, eventually it all worked out, even though they were, neither Salam nor Weinberg was convinced at the start that it sort of fit some things and not others, but in the end it fit everything. So the Higgs field was necessary in the Weinberg's construction and the Salam construction, because you needed it to solve these two problems where the W and Z bosons needed a stiffness, which was a bit mathematically and conceptually intricate, and you also need the electron and the muon and other particles to have a stiffness. And magically, one field, just one, was able to do all of it. And that is the case in the Standard Model. People very quickly realize you don't just, one field is maybe elegant and could have several such fields. Why just one? And those fields might not be elementary fields. They might be composite structures built out of new strong forces. And they might be associated with lots of other particles. I mean, just the idea that you take what we know about the Standard Model, even back then, maybe with a few extra things added, and you just stick in one Higgs field and it does the whole job. That was far from convincing because there was plenty of room for lots more. So what was predicted back in the 60s was that we need something to do the job that a single Higgs field can do, but maybe a whole bunch of fields are going to do. And particularly since you've got all these different masses. I mean, the top quark mass is 300,000 times larger than that of the electron. And we didn't even know then that neutrinos have mass. But now that we do know, I mean, that's another factor of 1 million or more from the electron down to the neutrino masses. The W and Z masses are up near the top quark mass. Why all this variety? Well, one possibility was that, well, there's all these different Higgs fields and they all do different things. And they explain why some things have a lot of mass, some have very little. So that was a question. Is it one Higgs field? Is it many Higgs fields? Are they elementary? Are they composite? Is there some more complicated story? Maybe more subtle. That was an experimental question for which we did not know the answer. So that's why when we turned on the Large Hadron Collider, which was let's say the third machine which had a shot of figuring this out. There were machines before which might have been able to figure it out if the Higgs, if things about the Higgs were a little bit more accessible, but it turned out they weren't. So you needed this big machine, the LHC. And when that turned on in 2010, we really didn't know what we were going to find. It might have taken many years to figure it out. But what do you know? The simple Standard Model with just one Higgs field is close enough to write. Not necessarily complete, but it's close enough that all the data we have so far, from the discovery in 2012 of the Higgs boson, the particle of the Higgs field, to all of the detailed studies that we've been making as we've been producing hundreds of thousands of these Higgs bosons and studying their various properties and so on. So far, this simple Standard Model with just one Higgs field that does the whole job is consistent with data. And now it's not as though we have high precision measurements yet. This is true at the sort of 10% level. So maybe when we get to the 3% or the 1% level, we're going to find it's not quite true. But as a first pass, for reasons we do not know, one single Higgs boson with nothing else attached fits the data. And that was not predicted. That was a possibility. But what was only predicted was there'd be something, not the details.
And what was found as of yet is just there's this single Higgs boson or the Higgs field that does the job. So maybe we can try to get into a bit of the details about how does the Higgs field work and what kind of properties does it have and how is it different than other kinds of fields that exist in the Standard Model?
Well, the Higgs field is special in a lot of different ways, which is, it's so weirdly special that there are a lot of reasons why people thought it wouldn't just be the Standard Model. Where shall we start? Well, the Higgs field, again, what I'm going to say about the Higgs field is something that many fields could have done. It could have been 7 Higgs fields rather than 1. But the important thing about Higgs-like fields, things that play the role of the Higgs, is that they have the ability to generate a restoring force for other fields. You could take a field like the electromagnetic field, which has no restoring force, and therefore its particles are massless. And if it interacts with the Higgs field in the right way, then under the right circumstances, which I'll describe in just a moment, the Higgs field can create a restoring force which changes how the field, how the other field vibrates. It changes its resonant frequency, which means that therefore its quanta, its particles, get mass that they didn't have before. So what happens with the W and Z fields is in the early universe, or in some abstract world where the Higgs field isn't doing anything or doesn't exist, the W and Z bosons are massless particles just like photons. But what happens is the Higgs field, in a sense, it switches on, or more precisely, it develops what's known as a vacuum expectation value, which means if you go and measure it in empty space, it's not zero. When it is not zero and it interacts with some other field, there's a possibility, depending on the nature of that interaction, that it's going to generate a restoring force for that field and therefore shift the frequencies and therefore the masses of the corresponding particles. And it turns out that in the Standard Model, one single Higgs field has the right properties that can do this for the W field, the Z field, all the quark fields, the electron field and its cousins, and the neutrino fields. All of them, which is not at all trivial because you can definitely write down universes where that would not work, where you would need multiple fields. Oh, and by the way, it also might be that you would write down a world like that, and unfortunately the photon would get a mass too. But no, this one and only one field has the property of the photon remains massless, and the gluons, the fields of the strong nuclear force, they remain massless. This is really very clever. This one field just does everything it's supposed to do and nothing that it isn't supposed to. And so this notion that the Higgs field, unlike the other fields of nature, if you go out into empty space, that means you take all of the particles out, you take everything out that can be removed. What remains in empty space is this whole bunch of field. And if you measure those fields in this chunk of empty space, they're all zero, except the Higgs field. The Higgs field is a vacuum expectation value. That is to say, it's not zero for some reason. We don't know why. We don't know why its vacuum expectation value has the size that it does, why it isn't much larger or much smaller. We can accommodate that. We can write down equations which sort of explain it, but the explanation has holes in it. We can't explain the hole. So it's not really an explanation. We just know experimentally this is a fact. There seems to be one Higgs field. We know it has a vacuum expectation value. That vacuum expectation value combined with the Higgs field's interactions with other fields is what gives them restoring forces and what gives the different particles of the Standard Model their masses. That's the big picture.
So the Higgs field itself turns out to create this ripple called the Higgs boson, and it itself has a mass as well. And it was
right. So let's talk about the Higgs boson, right? And it's not that the Higgs field creates a ripple, right? In the same sense, a string doesn't create a wave on the string. I can create a ripple in the Higgs field by whacking it somehow, right? And when we do particle physics experiments, you should think of it that way. We take two protons, we slam them together. Why? It's not because we're interested in what is inside the protons. We already know what's inside the protons. We're using these collisions as a way of disturbing the universe, as Freeman Dyson would say, right? We're trying to give it a whack and make it shake. And some small fraction of the time, we make the Higgs field shake. And when the Higgs field shakes, it makes a ripple. What's the ripple? Well, this is quantum physics. A ripple in the Higgs field is a particle. We have a name for it. It's called the Higgs boson. Okay, this is why we use proton-proton collisions to make Higgs bosons. We're trying to make the Higgs field ripple. Of course, if we succeed and we discover this Higgs boson, then we know that the Higgs field must exist. That's the logic. So the discovery of the Higgs boson, which was made through these proton collisions of two protons over and over again, finding a few that produce these ripples. The existence of the ripple proves the Higgs field exists. That's how we know now today that the Higgs field is not just something in somebody's imagination, but really exists in the world. So now, sorry, I've lost track of the original question.
So I want to focus in on this Higgs particle, or the ripple in the Higgs field, which is the Higgs boson. So it itself turns out to have mass.
Right. Right. Now, about the mass of the Higgs boson, that is one of the great mysteries in the following sense. So the Higgs field, as I said, has a vacuum expectation value. And now the Higgs boson corresponds to little ripples in that vacuum expectation value. So we want to know what is the restoring force that holds the Higgs field around its typical value. If I try to make it change a little bit, what vibration, what is the frequency of the vibration that I get? Well, this is tied in with the question of, well, why does the Higgs field have a vacuum expectation value in the first place? How do I think about that? And the answer is that, there's some dependence of the energy density of the whole universe on the vacuum expectation value of the Higgs. That is to say, if I tell you, suppose the Higgs vacuum expectation value were some particular number, you tell me how much energy density the universe has. And what the universe is going to do is it's going to look for the minimum of that energy density. Just the way lots of physics problems, the things after they settle out, they'll settle down in the minimum of energy. Well, the universe starts off at a big bang, things are really complicated, but over time, it's going to settle down to a place where the energy of the universe is minimized. And for some reason, the minimum energy density of the universe has the vacuum expectation value of the Higgs not being zero, something else. And why? Well, I don't know. So the question of why does the Higgs expectation value non-zero, and how much energy does it cost for me to shift it back and forth, is all tied up with the question of how does the universe's energy density depend on the expectation value of the Higgs field? And so what we thought was a question about the Higgs field is actually a question about the universe and its energy density. And that turns out to be very sensitive to details of quantum physics. So on the one hand, if I'm naive and I say, forget about this quantum physics, there's some potential energy density for the universe. It comes from somewhere. I find the minimum. That tells me what the Higgs expectation value is. I look at how curved it is at the bottom of the minimum. That'll tell me how fast the Higgs field would move back and forth. It tells me about the restoring force. That tells me the mass of the Higgs boson. So from the point of view of equations, it's simple enough. But the question is, where does that potential energy density come from? And the problem is, I don't know, because it's affected by quantum fluctuations, by the quantum interactions between the top quark field and the Higgs field. It's affected by the interactions between the W field and the Higgs field. It's affected by the Higgs field's interactions with itself. It's affected by the electron field's interactions with the Higgs field. So on the one hand, the Higgs field, through its vacuum expectation value and its interaction with the electron field, is giving the electron field its restoring force, and thereby the electron its mass. But the electron field then comes along and says, yeah, but I'm interacting with you. I'm going to change your energy. And so you have to combine the electron field's interaction, the top quark field's interaction, all those interactions, you have to put them all together and compute in some self-consistent way what the potential energy is for the Higgs, and then find out, okay, where does it want to settle down? So it's a coupled problem. Your equations have the Higgs field affecting the electron field, but the electron field affects the Higgs field. It even turns out that the electron field's effect, even though we set up the whole Higgs mechanism, the whole idea was set up so that the Higgs field would determine the masses, would help determine the masses of all these other fields, determine the frequencies of all the other fields, and therefore the masses of the corresponding particles. It turns out that the other fields affect the Higgs field even more. And so the whole story of how this works becomes a very complicated problem. And so on the one hand, if we just sort of accept that, all right, well, it solves itself somehow, and the potential energy for the Higgs field is something, and the minimum of the potential gives us the Higgs expectation value, and the curvature of the potential gives us how fast the frequency is for the fluctuations of the Higgs field, and that tells us the mass of the Higgs boson. Okay, fine, we understand it. But the problem is we really don't, because we don't know where that energy density came from. And to calculate it, we first of all have to account for all of the quantum corrections. And we also have to account for any quantum corrections which come from effects that we don't yet know about, like effects from quantum gravity. Those can be important too. So we actually can't calculate it. And then it gets worse, because there's something very strange about the Standard Model that's buried in the existence of this Higgs potential, the potential energy density that affects the Higgs so much. It's buried in there. And you have to think about it for a minute to realize how serious it is. And this is tied up with something called the hierarchy puzzle, which I can say some words about if you like.
Please, yes. So to summarize it, up to this point, the Higgs is giving particles this stiffening, this restoring force, which gives them some natural frequency, which leads to their mass. But then there is sort of a back reaction or an effect, a counter effect, where now they are interacting with the Higgs. And so its energy density perhaps should be large, really large maybe. But there's this effect backwards.
Right. Well, so there's the question of where there's two questions. How big is the energy density that you end up with? But the question we're really asking here is, where is the minimum of the energy density? Because that determines the size of the Higgs field's expectation value. And there's a lot of different ways to phrase this puzzle, the hierarchy puzzle, and different people phrase it different ways. I will give you a very physical way of thinking about it, which I think is most useful. And that's the following, that one should understand this as being a question that is not so different from asking about a phase transition in a metal. Okay, I think some metal, it's got a solid phase, it's got a liquid phase. There's some transition between the two. So in the case of the liquid or solid, it's a transition temperature. But you know, the temperature also depends on impurity. The melting temperature depends on impurity. So in general, a transition temperature can depend on a lot of different things. Now in the Standard Model, there are also multiple phases. For example, if there were a phase of the theory where the Higgs vacuum expectation value were 0, then the W and the Z fields wouldn't have any restoring force. The W and Z bosons would be massless. So that's a phase of the theory where the W and Zs are massless. And there's a lot of different ways that that we could arrange that the Higgs field vacuum expectation value is 0. We just have to have a minimum of the energy density such that the Higgs vacuum expectation value sits at 0. And then we could change that potential in lots of other ways, but as long as the minimum stays at 0, we're in this phase with massless W's and Z's. So there's this big expanse in terms of all the different ways we could arrange the Standard Model such that the Higgs field's expectation value is 0, and we're in the massless W and Z phase. And then there's some transition I can make where I change the parameters of the Standard Model And now suddenly the Higgs vacuum expectation value is not zero. It could be small, it could be medium, it could be large. But in this phase, the W and Z bosons have a mass, and those masses could be small or medium or large. So again, there's a big phase with lots of different details where we have massless W bosons, and there's some transition, and below that transition, the W's and Z's are massless. Not so different from solids, liquids, and some transition in the space of parameters. So imagine that you walked into a colleague's laboratory. Your colleague is a solid state physicist, and they're studying the melting temperature of some particular material. And they've been gone for weeks. So the system is sort of, out of equilibrium a little bit, and things are moving around. It's not the way they left it. And you walk in, and what do you know? The experiment has just at the moment you happen to walk in, the temperature at which the experiment is sitting is right at the melting point, to within 1 part. It's not exactly the melting point. It's just above the melting point by 1 part in 10 to the 12. You say that's kind of weird. I mean, how did it get there? Why is it so close? Why is this material sitting right next to its transition temperature? Well, I mean, there's an obvious answer. The experimenter who runs the lab tuned the parameters of the experiment, tuned the temperature and the pressure and so forth, so that the experiment would sit right there, and then arranged it would stay there. And okay, so it's not an accident. It was set that way. So if there's an intelligent designer of the experiment, you're not surprised. But, the universe, maybe it was intelligently designed, but most scientists would assume that that's a cop-out. And most properties of the universe should have an explanation, which is a mechanistic or historical explanation. So when we go to the Standard Model and we look at the fact that, yes, the W and Z bosons have a mass, we're in the massive phase, but relative to how big those masses could be, well, we don't really know this. So put a star by this. This is under the assumption that the Standard Model is right and you add gravity and there's nothing else. There's a natural scale in the world, which is the scale of it is the mass of the lightest possible black hole, called the Planck mass, or corresponding Planck energy by adding c squared, or corresponding length by doing quantum mechanics and converting energies and times to length, energies and momenta to length. If the W bosons and Z bosons had the Planck scale mass, that would mean they were 10 to the 15 times higher. So now here's the question. If the masses could be that high, and remembering that the energy density of the universe is very sensitive to all these different effects from the top quark field, effects from the electron field, even effects from quantum gravity we don't know, why are the W and Z boson masses 10 to the 15 times smaller than the Planck mass, sitting right next to the phase transition, just above it, not on it, right next to it? Why are we so close to a phase transition? To the degree that if you walked into somebody's lab and you find a piece of material sitting there, you'd say, oh, obviously they set it that way. How else could it get that way? So this is one way to understand the hierarchy puzzle. We sit very close to a phase transition. Very, very, very close. So is the argument naive? Is there a mechanism which explains why this is true? Are we thinking about it the wrong way? And, one point of view is, look, in the laboratory, you've got all these knobs you can tune. There's all these different materials that you could be running your experiment on. There's all these options. There's only one universe. So we don't have to explain this. It doesn't require an explanation. It's one universe. It has these properties and we're done. But this has never really been a successful way to think in physics in the past. I mean, normally when we find something which is so close to a phase transition, or another way to say it is, it's sort of a dimensional analysis question for those who understand how dimensional analysis works. When you find a dimensionless number in nature, some ratio of things that you can write as a number with no units, either that number tends to be, close to 1, maybe it's 100, maybe it's 10, maybe it's a tenth, but usually it's, 2 or 2 pi or something. And when it's really small or really large, there's usually an explanation if you work hard enough. So here we have a number which is 10 to the minus 15, or in some languages, you would really say it's the square of that. Shouldn't there be an explanation? Oh, there's no guarantee that there's an explanation. It's a puzzle worthy of trying to explain, for sure, because it's of the same, it's the same type of any dimensional analysis problem. So now there have been all sorts of attempts to solve it. Most of those solutions make the prediction that there should be things other than the Higgs boson discovered at the Large Hadron Collider, and this has not happened.
Famously, supersymmetry is one of those theories.
So supersymmetry is the idea that for every effect on the energy density of the universe that comes from the known particles, there's some unknown particle which mostly cancels off the effect. So for the top quark, which has a big effect on the Higgs, big effect on the energy density of the universe, there's a top squark, which is a boson, while the top quark is a fermion. Their effects come with opposite sign. They mostly cancel as long as the top quark and top squark do not differ in mass by very much more than the Higgs boson's mass itself. And since the Higgs boson's mass is 125 GeV from experiment, meaning about 130 times the mass of a proton, we should find the top squark with a mass within a factor of 3 or 4 of the mass of the Higgs boson. This has not happened. And there should be similar partner particles for all of the existing known particles, or the supersymmetry mechanism for doing these cancellations just doesn't work. And none of them have shown up. Nice idea, doesn't seem to be true. Another idea was one I mentioned, that the Higgs boson and the Higgs field, they are composite. They are made by taking other simpler fields and somehow mashing them together with a new strong force of some type. But again, under such circumstances, we would expect the Standard Model's prediction for the Higgs field to differ from the data by at least 10% or more. And we see no such effects. In fact, we would really have expected effects that are 50% or more. Big effects. Nothing is seen at that level. So that idea, which would also solve the hierarchy problem, because it would say that our naive sense that there's this phase transition, then we could move the W and Z boson masses up by 15 orders of magnitude, by a factor of 10 to the 15. Well, that's wrong, because the whole picture breaks down, because the Higgs field is not as simple as you think. Those are phase structures different. There's probably some other phase transitions. This picture was naive. Well, the compositeness of the Higgs field would indeed address the hierarchy problem, would change it, we'd have to rethink it, but we see no sign of it. So now what other solutions exist? Well, one idea is that it's a historical effect. So what do I mean by that? Well, there's a famous fact about avalanches, that if you look at a slope of a sand pile or of snow, it's very common to find it just about to avalanche, which means if you ski on it at all, you're going to trigger it. There's sort of a transition. There's a slope beyond which it'll avalanche, and if it's below that slope, it won't avalanche. So why is it you always find the snow ready to go? Well, the reason is, if it's beyond the point that it's ready to go, it'll avalanche. And it'll stop avalanching when it finds a slope where it's no longer going to avalanche. So it naturally pushes itself right to the boundary between two phases and stops. And until you push it over, it won't avalanche again. So maybe there's some historical effect that pushes the universe, pushes the parameters of the universe, pushes the energy density of the Higgs field in such a way that it ends up just beyond a phase transition. This is known as self-organized criticality. And there are a couple of theories of this. They never really work. And the reason is, they might work, but you're going to have to do something else too, because they only work by adjusting the energy density of the universe so that the expectation value of the Higgs comes out right, but the overall energy density at that minimum cannot simultaneously be adjusted. So that we get the Higgs field right, but the total energy density of the universe comes out to be whatever it is, and that's a problem, because we have another issue in the universe that we haven't dealt with here, which is the cosmological constant. And that's the problem, that if there's any significant amount of energy density in the universe, if that energy density, total energy density, no matter how we got to the minimum, once we're at the minimum, we ask how much energy density is there. If it's positive, the universe expands outward so fast, there's no time to make galaxies, stars, or life. And if it's negative, the universe immediately collapses. So somehow we're in a universe where the energy density is extremely small. We're even closer to a phase transition in the case of the cosmological constant. So the problem is, how do you set up a theory where the Higgs field ends up very close to its phase transition and the cosmological constant ends up very close to its phase transition at the same time? And in my opinion, there is no solution, no historical solution, which does both of those at the same time, that ties the two problems together in some way.
So you're saying that the hierarchy problem, this issue with the Higgs field, and the cosmological constant problem, the issue with the energy density of the entire universe, might not be related. These are separate problems.
It's almost, well, I'd say it differently. No one has succeeded in showing how they are related. And without some way to tie them together logically, your solution of one ruins the other, typically. There's no solution that's out there that gets both of them at the same time. This is actually a subtle point. It's sort of a discussion of its own. But in my opinion, there is no such solution. And a substantial fraction of physicists agree on that, although there are some who would argue otherwise, but I could tell you why they're wrong if we had more time.
Yeah, so I would have loved to have gone into more detail into the cosmological constant problem and the hierarchy problem. What I want to end on here, just to wrap it all up, is these days the LHC, the Large Hadron Collider, which was the machine that discovered the Higgs, is still running, and it was looking for other particles. They didn't show up, as you said. A lot of people have recently come to question, what is the LHC doing right now? What is it trying to look for? How would you maybe defend or describe the objectives of the LHC right now and where it's going? And maybe we can wrap it all up in talking about the machine that actually discovered the Higgs.
Yeah, I mean, I don't think it needs defense, but I will describe it. I mean, what we know from LHC data is that there are certain classes of particles that would have shown up by now and have not. But there are other classes of particles that wouldn't have shown up yet, partly because either because they're rare in production, or they are very hard to detect because the signatures that they leave have very large backgrounds from standard model processes and make them tricky to discover. And there are huge classes of such particles. In particular, if particles are produced via the strong nuclear force, then when you're smashing protons together, and the protons are held together by particles that feel the strong nuclear force, and that's easy. You make particles with strong nuclear forces in abundance. So if there were particles of that type, we probably would have found them by now. If there are particles that only interact by the weak nuclear force, well, the limits are not nearly as good. So those could sneak by if they're sufficiently heavy, and we're still looking for those. But what about particles that do not carry the strong nuclear force, the weak nuclear force, or the electromagnetic force? Well, why would we think any such thing exists? The one thing we do have some evidence for is there's something going out in empty space that causes it to appear that there's something we call dark matter. So without getting to the argument of whether dark matter exists or not, we have evidence of something that doesn't carry standard model quantum numbers, even if it's some weird effect that isn't literally dark matter. And if it is dark matter, maybe it's made of particles, maybe it's not. But certainly there's evidence in nature that we ought to be thinking about the possibility there might be particles that don't carry any of the known forces other than gravity. Such particles would be very difficult to produce at the Large Hadron Collider, but in many cases not impossible, because of other interactions they may have. For example, they may have interactions with the Higgs field indirectly, or there may be other particles we haven't discovered yet, which allow them to interact, at least these otherwise dark particles to interact with us. And those dark particles, whether they're dark, how do we observe them? They go right through our detectors. Well, again, if there are interactions which allow them to be produced, there are also going to be interactions, the same interactions in many cases, may allow them to decay to particles that we can observe, and to do so fast enough that we would see them at the LHC. And one of the major areas of my research, going back to 2006 with Catherine Zurek, who's a professor at Caltech now, one of the major areas of our research was to point out that if you have this scenario where there are particles that can be produced and then can decay back, which don't carry any of the known forces, but have forces of their own, you can get a wide variety of weird, complicated signatures, and the rates for this production can be quite low. This can affect the Higgs field. The Higgs field can therefore have weird decays that are not predicted by the standard model. And there are other processes which can occur. And looking for these is something which, first of all, was not really planned for when the LHC was designed. So sometimes the detectors are not really built for this. You have to work around their limitation. People didn't view this as a priority because so many people were gung-ho about supersymmetry, so they all went and looked for that first, and now they're only coming back to this question now, 15 years after we suggested it. And there's a very wide variety of these signatures, so there are a lot of searches that still have to be done. And this stuff can hide in the data. You can have a huge data pile and look at it all sorts of different ways and still miss this stuff. You have to learn how to do these searches and how to target these types of phenomena. So this is still ongoing and far from complete. There's a whole research program on this. And so any conclusion that the Large Hadron Collider is looked for everything and there's nothing there, that is way premature. On top of that, there are precision measurements that the Large Hadron Collider can and should do. We do have this new particle, the Higgs boson. We should study it to death. We should learn everything about it that we can. And that requires making lots of them and studying them very carefully. And the more carefully we want to make the measurements, the more difficult the measurements become, and the more careful we have to be. So that takes time, and we're not just The experimenters are not just collecting data, they're learning how to use their data more effectively. And so it's not just a matter of sitting there, okay, next week I'll come back and see how many more events do I have. It's also, how can I remove the backgrounds more efficiently? How can I be more precise about how I do so? And so the methods are always improving. And the detectors are going to be upgraded so that when we get more Higgs bosons with a higher rate in the future, we'll also have detectors that are more efficient at picking them out. So people are not sitting on their laurels here. They are improving the methods all the time.
I completely agree with that description. This has been an absolutely delightful conversation, incredibly clear and just beautiful explanations of the physics. I highly recommend people to get the book, Waves in an Impossible Sea. And you also write on a blog of particular significance, right? I've been following recently your blog posts concerning you trying to tackle now the understanding of the 1920s quantum theory and the wave functions and eventually how they relate to quantum field theory. So I highly recommend people go check out your blog where you write about all sorts of things related to particle physics, quantum theory, quantum field theory, and it's just a delight to read. So Professor Matt Strassler, thank you so much for joining me today.
It's been a pleasure. Thank you so much for the invitation.
Thank you.